Hi, everybody, and welcome to our review session for the third exam. Um, there's not anyone with me live today, and I was a little afraid of that because I wasn't able to do it in the evening like I was the previous times. So I'm just going to walk through a number of questions um, from the practice questions uh, that I sent you a WAMAT message about. And we'll also start by talking about just kind of general strategy when you are approaching the kinds of hypothesis tests and confidence intervals you're going to be asked to do on this third exam. So let me share my screen here. And the first thing I want to just point out, as always, right, is the time for the exam. So, Yakima students, you can take the exam on the 31st. That's a Sunday during the hours that the Yakima Proctoring Center is open on that day. Or you can go in on Monday, either in Grandview or in Yakima. I also am allowing you to take the exam on Tuesday the 2nd. So there's actually 3 different days that you can choose to take exam number 3. Um, Going down here to the chapters 3 and 4 exam information, here's the document we're going to be going through today. What I would suggest is after I do my introduction here, I would pause this video and try the problems yourself first. Um, as you're working on the problems, understand that these are the formulas that you'll be given on your exam. So this document will be attached to the written work portion that you'll get from the test proctoring center. So all of this will be at your disposal. All right. And let's see, there was one other thing. Yes. The inference review, exam 3 inference review. So these are different questions than I'll be going over today. And it's a long packet of problems for you to go through and just work on your own. And the key for those problems is down here. Now, it's important to understand that when you're comparing what you've done to the key for this long review assignment, that being off from me by a decimal point or so is fine, right? That's going to be due to us rounding a little bit differently as we proceed through the question. So don't be alarmed by that. But this packet will really help you feel prepared for the third exam. So don't save it to the last minute. It does take a long time. I believe there are 9 full questions in there. And some of those questions ask you both to do a hypothesis test and a confidence interval. All right, so just be aware of that that's something you want to start um, early, not late. Okay. Then the last thing I want to say is if you do choose to take exam number 3 on Tuesday the 2nd, just understand you do have quite a bit of chapter 5 material due in quick succession here on Wednesday, Thursday, and Friday next week. So you're going to want to get a good start on that well ahead of time. You can see that I've scheduled you to do some chapter 5 material at the end of this week, and that's not going to appear on your third exam. That'll appear on your final, but just you might want to be doing some chapter 5 homework and things if you wait until Tuesday to take that exam, just because you're going to have quite a bit due in this little bit of time. Okay. So before we actually do any of the questions, I want to just uh, I just want to kind of step back and say, what is it that I'm expecting of you here on this third exam? It's really simple. I'm going to ask you confidence interval questions and hypothesis test questions, but you're not going to know what type of confidence interval and what type of hypothesis test to do. So when you're presented with the information, you have to decide, am I doing a single proportion hypothesis test? Am I doing a 2 independent mean hypothesis test, right? We have all these different types of hypothesis tests, and all these different types of, well, I guess 2 different types of confidence interval, right? One for proportions, one for means. And I have to decide which one is appropriate for the situation that I'm given. So what I want to start with before we do any practice questions at all is just to kind of go through a flow chart here. Now, this isn't a flow chart that I'm going to provide for you, but if you kind of think through this flow chart as you are doing all of your practice uh, problems, then I think this will really help you. So, the first question I want you to ask when you're given a hypothesis test is I want you to ask, what type of data am I presented with? What is the data type? Now, we know there are two types of data that we could be presented with. On the one hand, it could be categorical. And on the other hand, it could be numerical. So that's always the first question I want you to ask is, what type of data do I have? And remember that the little thought experiment that you can do in order to determine that correctly is to say, if I'm the person walking around with a clipboard, what am I writing down as I collect data? Am I writing down a bunch of words? Well, then that means the data is categorical. Am I writing down a bunch of numbers? Then it's numerical. All right. So after what type of data, there's another question you need to ask, and that is, how many sample groups? Yeah. And you're going to ask that whether it's categorical or numerical. Often, when we do a hypothesis test, we are simply given one sample group, right? Information about one sample has been collected. But we've also had ones where we're comparing two groups to one another. So let's stick to this side with our categorical data. And let's talk about what happens when we have one sample group versus when we have two sample groups. So if I have one sample group with categorical data, then I know that I am doing a one proportion hypothesis test. And the moment that I see that, I go ahead and go to my formula sheet here, and I can see that under hypothesis tests, I've determined that I'm doing a single proportion test. And so this is the type of test where I want you to actually use the formulas. I want you to calculate the standard error. I want you to calculate the test statistic, and then I want you to use the normal probability calculator to find your p-value. All right, so just to kind of summarize, this would be one where your null hypothesis is that p is equal to the null value, right? We use a little p0 there. And you're going to use standard error is the null value times 1 minus the null value over the sample size. You'll then plug your standard error into this formula. Remember, p with a little hat is your sample proportion minus your null value divided by your standard error. And then finally, use the normal probability calculator. To find the p-value. So that's what I'm going to want you to do. If you realize it's categorical data, determine that there is only one sample group, then I want you to do a one proportion hypothesis test with these formulas and your normal probability calculator. Okay. What if it's two sample groups? Then this is a two proportion test, of course. And while there are formulas for the standard error, and so this would be where the proportion for group number one is equal to the proportion for group number 2. So if this is my null hypothesis here, then yes, there are formulas that uh, that I could use that are just a little bit more complicated than, say, this standard error formula. But rather than messing with all those, remember, I've given us permission to, for a two proportion test, use the theory-based inference applet. Okay. So we'll just say use the theory-based applet. To find your p-value. Okay. So we've covered what we do if we get categorical data. Okay, but what about numerical data? Once we answer the question of the number of sample groups, there's going to be one more question we're going to ask if there happen to be two of them. Okay. So if there happens to be two sample groups, we'll ask one more question, and that is the data paired or not paired? There's our question. And so based upon whether it's paired or not paired, that'll determine where we go from there. All right. But let's talk about if there's one sample group. Then this is just going to be a single mean test. And like with the single proportion test, I'm going to want you to use formulas that I provide and a calculator in order to do this problem. So this would be if my null hypothesis was something like the mean is equal to some number. Once again, I can go back to my formula sheet and I can see for a single mean test, we have a standard error that's standard deviation of the sample divided by the square root of the sample size. And then here's my test statistic formula. So those are the ones I want you to use in this instance. So sample mean minus the null value divided by our standard error. All right. And then finally, once we have that test statistic, we can plug it into a calculator, but this time it's not the normal probability calculator, right? This time it's the t probability calculator. Right? Anytime we're dealing with numerical data, we're using the t distribution. Okay. So numerical data with one sample group, we're going to run through these formulas and calculate our p-value with the t probability calculator. All right. Now, if there are two groups, we'd have to ask one additional question, right? Is the data paired or is it not paired? So remember, paired means that every member of one group, it makes sense to pair them up with a specific member of the other sample group. So first of all, your two sample groups have to have the exact same number of people for you to even entertain the idea that they might be paired. But it goes beyond that. You also want to make sure that it makes sense to have a connection. So this often takes place when you have kind of like a before and after sort of a situation, right? Where maybe there's a data point that's connected to the same person in a before sample and an after sample. So things like that. So when we set up our hypothesis here, all right, sorry, just thought I was going to sneeze there. Then we're talking about, we're testing the mean of differences, and we're saying, okay, the mean of differences we're going to assume is 0. If you get paired data, though, I do not need you to use a bunch of formulas. Once again, you can use the theory-based applet. To find the p-value. But I think what's worth saying is that this theory-based applet, to find the p-value, you're going to do a single mean test on the differences in that theory-based applet. All right. And then if the data is not paired, then you have a 2 independent mean hypothesis test. So your null hypothesis would look something more like this, where you're saying the mean for one group is equal to the mean for the other group. And again, use the theory-based applet for that. So I think you'll find this process of kind of working through this in a flowchart type manner. Let me zoom out just a little bit. I think you'll find it helpful, right? So the questions are, first, what type of data is it? That helps you narrow down which side you're on. How many sample groups? You're going to ask that regardless of whether it was categorical or numerical data. And then only in the case of if there are 2 sample groups on the numerical side, do you have one more question to ask, and that is the data paired or is it not paired? Okay. So let's do some practice. Now, I do want to say that of all the things I could ask you to do on this exam, I'd say there's 7. I could ask you to do a confidence interval for means, a confidence interval for proportions, and then I could ask you to do one of these 5 types of hypothesis test here, right? So a total of 7. So in this practice set of questions, I'm not going to cover all 7. So just please be aware of that. Between this and then the inference review packet that you'll work on between now and the exam, that'll cover everything probably multiple times, okay? So you're going to get plenty of practice on everything, but just please note that I'm only going to ask 5 questions today. That's what we're going to do. So I'm not going to cover every single possibility. All right, so we're going to start here with number 1. A medical researcher measured the body temperatures of a sample of 22 randomly selected adults. The sample mean was 98.3 degrees and the standard deviation 0.6. We're told here that the body temperatures of healthy adults are approximately normal. Create a 95% confidence interval for the average body temperature. Now, this one is asking for a confidence interval, not a hypothesis test, but we can still use the same first question that we did in that flowchart. I can still ask the question, what type of data is it? Okay. Well, we're talking about body temperature, so I'm walking around with my clipboard and I'm writing down a bunch of numbers, right? So I know it's numerical data. And so even though this isn't a hypothesis test, that's still really helpful because I can go up here to confidence intervals and I can see, here's my confidence interval for means, because means always go with numerical data. So I'm just going to grab these and paste them onto my paper here. All right, so we can see the things that we're going to need. But before we get started on any calculations, let's talk about our conditions. Always check that first. And these conditions are the same, whether I'm doing a confidence interval for numerical data or I'm doing a hypothesis test for numerical data. So remember that number 1 is we want to make sure that we are sampling less than 10% of the population. And here that's an obvious one because definitely 22 people is less than 10% of adults. That's not going to be a problem. So that condition easily checks out. Now, number two, remember that one is the population needs to be nearly normal. It needs to not have a strong skew in it. We don't have access to what the population looks like, and we don't even have access to exactly what the sample looks like, which is what we often use to make a guess about the population, right? You look at a histogram of our data and use that as evidence as to whether the second condition is met. We don't have that this time, but they did tell us, and remember when we studied normal distributions, we said that things that occur naturally do tend to follow a normal distribution a lot of the time. So we could just say this. We were told population of body temperatures is normally distributed. So neither one of these are controversial at all. Didn't have to think about either of them too hard, but we need to take a moment just to check those conditions. Okay, so now we can go to the calculations, right? So we can see the things we need, right? We need a sample mean. Well, we were just given that directly, right? 98.3. We need a standard error. So standard error, of course, is our sample standard deviation. So that would be 0.6 divided by the square root of our sample size, which is 22. So our standard error is approximately what in this case? Let's see. I didn't bother to actually calculate that. So let's do that right now. So 0.6 divided by square root of 22. So 0.1272. Okay. So then the only thing left is my T star. So remember what we're doing is we are saying, I want to figure out what T star ought to be so that when I sketch this picture of the sampling distribution, that going down that amount and going up that amount will encompass the correct percentage of the sampling distribution, right? Since we're doing a 95% confidence interval, that means we want 95 in the middle. All right. So this is a job for our T distribution, right? So we'll go to our T probability calculator. But remember, the T probability calculator only allows you to shade one side or the other, correct? Also, our T probability calculator needs degrees of freedom. So before we get too carried away with using this calculator, we come back here and we say, all right, I also need my degrees of freedom. And remember, that's one less than your sample size. So 21 is what I'm putting into that spot. Okay, and then since I need to shade one side or the other, knowing that 95% is in the middle isn't really helpful. What I really need to know is how much is out on these edges. But since it all has to add up to 100%, that means I've got 5% split between the lower and the upper, which would give me half of that, 0.025 or 2.5% on each tail. And so now I can go to my calculator and type in 0.025. And then it tells me that my T value that accomplishes that gives me exactly 0.025 to the right in this tail, is a T value of 2.080. T star. So, excuse me, now we can put it all together, right? The interval is made by taking your sample mean, 98.3, adding and subtracting t star, which is 2.08, times my standard error, 0.12792. 8.3 plus or minus 0.266. And so let's remember that we're quite literally doing 98.3 minus 0.266, and we're doing 98.3 plus 0.266 to make my interval. So I end up with 98.03 degrees Fahrenheit up to, let's see, 98.3 plus 0.266. So 98.57 degrees Fahrenheit. So that's our 95% confidence interval. Okay. Whether I ask you a confidence interval question about means using numerical data or about proportions with categorical data, I need you to be able to give me a sentence that helps me understand that you know what a confidence interval is all about. So explain what our interval means in the context of this situation, right? So this is a range of values that we're estimating the true mean body temperature is between, right? So we're not certain of this, but we're pretty certain. In fact, we are 95% confident, right? We're 95% sure that the average body temperature for adults is between 98.03 degrees and 98.57 degrees. Notice that my interval, I'm writing this, interpreting it as I'm estimating this is what the population body temperature is, right? So your interpretation of your interval is not about your sample. We know exactly what happened in the sample, right? In the sample, we got 98.3 degrees. What we're interested in here is, saying, I am making an estimate for the average body temperature of everyone, of all adults. All right, then part C. Would a 99% confidence interval be wider or narrower than your answer in part A? This would be a good time to pause and think about it for yourself first. But there's really two ways I would kind of explain this, right? One is just to kind of reason my way through it without getting too technical with any of my explanation. We could say something like, in order to be more confident that we capture the true mean, with our interval, we should include a wider range of values. Makes sense, right? It's kind of like going with the idea, that I have discussed, in the videos and things, that if you want to be more sure you catch a fish, throw out a wider net. A little bit more of a mathematical approach to it would be to talk about the fact that when you change your confidence level, T star changes, right? So you could look at this picture here and imagine that if this was 99, the only way for the region in the middle to be 99% of that region would be for you to have to widen out a little bit, right? So the other reason is that T star must be greater for a 99% interval, making the interval wider. Okay. So that was a confidence interval question. I could certainly ask you a confidence interval question for proportions. I did not in this practice, in this particular set of practice questions, I didn't have one of those. So just be aware of that and make sure you practice plenty. And you'll get the opportunity to as you work through the inference review packet, but make sure you're practicing some proportion confidence intervals. All right, so let's look at number 2. It says in a Rasmussen poll of 1,000 adults in July 2010, 520 of those polled said that schools should ban sugary snacks and soft drinks. Do a majority of adults, which means, of course, more than 50%, support a ban on sugary snacks and soft drinks? Perform a hypothesis test using a significance level of 5%. All right, now, I mentioned this in the videos, and I just will reiterate it here, that I am okay when you state your null and alternative hypothesis. I don't always need you to write it out what your hypotheses are in a sentence unless I specifically ask you to. So what I'm okay with here is just let's make clear what our parameter value is. I'm getting a little ahead of myself. I'm sorry. But let's make clear what our parameter value is, describe that, and then go ahead and write our null and alternative hypotheses and symbols. All right. But they're talking about a hypothesis test. So let's go through our flow chart. Okay. So they're asking people, should they ban sugary snacks and soft drinks? Okay. So first question, what type of data? I've got the clipboard. I'm writing things down. What are people telling me? They're telling me yes, no, maybe not sure. So I'm writing down categories. I'm not writing down numbers. So that tells me it's categorical data, right? So I'm over here. How many sample groups are there? Well, all they did was ask a bunch of adults. There weren't 2 different groups of adults. It was just one big group of 1,000 adults. So that means there's 1. So this is a 1 proportion test, and I'm using these formulas here along with the normal probability calculator to find the p-value. In terms of my formula sheet, it's a single proportion test, so I'm right here. It's reminding me of how to calculate the standard error and the test statistic. Right now, that's good that I've determined that, but I'm not going to just start computing formulas. Now I'm going to actually slow down and say, all right, let's set up my hypotheses. So the moment that I understood that it was a test of proportions, I'm going to use P. That's why I said I got ahead of myself a moment ago. So P is the proportion of adults who favor banning, and just for the sake of brevity, let's just say junk food. Let's just include sugary snacks and soft drinks. Actually, you know what? Let me model good behavior here. I wanted to write less, but that's not good because junk food's really bigger than that, right? That's like chips and things like of that nature. So let's be clear. Sugary snacks and soft drinks. Now that I've clearly identified what this P is, now it's okay if you just want to write in symbols the null alternative, that's fine. So we're trying to prove that it's more than 50%. So that means we should start by assuming it is 50%, right? Our null hypothesis always contains the equal sign. And so my alternative here is that it's more than 50%, so greater than 0.5. All right, so part B asks, are the appropriate conditions met? And remember, it doesn't matter what confidence interval you're talking about, what hypothesis test type you're talking about. The first condition you're checking is always the same, right? Do we have that independence condition, which means we're saying, are we sampling less than 10% of our population? And in this case, our population is adults, right? So easy to say that 1,000 adults is a lot, but way less than 10% of our population. All right, number 2. So remember that when it's proportions, the condition is different. The second condition is different than when it's means. For proportions, we have to check the success failure condition, right? And the success failure condition asks you to take whatever your null value is and multiply it by your sample size, right? So the null value times your sample size is 500. And I'm going to do something that's going to seem silly, but I'm just going to be thorough about it. In this instance, this is not really necessary because it's a 50-50 proposition, but technically you're supposed to do the null value and then 1 minus the null value times your sample size. Of course, the reason that's silly in this case is because it's, of course, the same. But the key here is that this means we expect 500 successes and 500 failures. Okay, so remember what we had to expect? 10. So this one's no problem, right? As long as it's more than 10 on both counts. All right, so now we can start using formulas, right? What's our sample proportion, right? We might also call this, remember, the point estimate is another way it could be asked of us. And of course, that's just what happened in our study, right? Well, out of 1,000, 520 said yes, right? So that's 0.52, right? My standard error. Okay. Again, we can look that up. Don't have to memorize it. It's my null value times 1 minus my null value divided by my sample size. Then I'm going to take the square root of all that, right? Null value times 1 minus my null value divided by 1,000, right? And I did not do this ahead of time, or I did it ahead of time, but my paper got cut off. So let's see. Here's my standard error, 0.0158. All right. So my test statistic here, so that's our z-score in this case, is given by sample proportion minus the null value divided by that standard error that we just calculated. So z is 0.52 minus the null value of 0.5 divided by 0.0158. So there's my test statistic. Now remember that the whole purpose of our test statistic is to tell us where we are on a sampling distribution. So think back to when we were doing simulations, right? We had to know where to go in the simulations to start counting up all the times in the simulations that we got results like ours or even more unexpected, right? If the null were true. So we're expecting that our sampling distribution would follow a normal curve. We have 1.266. That's the locator. That tells me where I'm at. Let's put it right about here, 1.266. And the idea is I am needing to find this, right? How much of my sampling distribution is at where my sample was, which is 1.266 for a test statistic, where mine was, or even further from what was expected, right? And what was expected is right here in the middle. So how often does that happen, right? When you're just sampling randomly from a population where the null is true. So this is where we'll go ahead and pull out our normal probability calculator, right? Normal distribution is what we use for proportions. It goes with z-scores. And so let me go ahead and open that one up. And so remember, no degree of freedom here. It's not part of a normal distribution. So we'll shade the correct side, and then we'll put 1.266 for our z. And there we go. We get a probability of 0.1028. So there's our p-value. All right, so we've gotten that. What does that mean again, right? If the null were true, we expect to see sample results like ours or ones that are even further from the null about 10% of the time. And while that may not sound like a lot, it's it's not unexpected enough for me to throw away my null hypothesis. In other words, it's a little too easy for samples like mine to just come up due to random chance. And so because of that, we're going to fail to reject the null. And we're doing that since our p-value is greater than our level of significance, which was 0.05 in this case. Okay. Down at the bottom here, I'm just going to remind you of the template that we're always going to use here, right? This is not my answer. This is the template we want to use, right? There is / isn't enough evidence to suggest that the alternative is true. And remember that it's precisely when we reject the null that we say there is enough evidence for the alternative. And when we fail to reject the null, that's when there isn't enough evidence for the alternative, right? Because the null and alternative are set up in opposition to one another. So if we reject, there is enough evidence for the alternative. If we don't reject the null, then there's not. So this is definitely a case of there is not. So there is not enough evidence. At the 5% level of significance, to suggest, well, to suggest the alternative is true, but we're not going to say that, right? We're going to put it in context, right? We're going to make it so that anyone reading this, regardless of if they've taken statistics or not, would understand our conclusion, right? So our alternative was that, let's go back up here. You can always kind of copy from yourself, right? That the majority of adults support a ban, right? So there's not enough evidence to suggest the majority of adults support a ban on sugary snacks and soft drinks. Okay. Let's take a look at another one. The paper, Pathological Video Game Use Among Youth Ages 8 to 18, a national study, included the information in the table below about video game playing time for representative samples of 588 males and 590 females selected from U.S. residents age 8 to 18. Carry out a hypothesis test to determine if there is convincing evidence that the average number of hours per week spent playing video games by females is different than the average number of hours spent by males. Okay, let's go through our process. Talking about video game playing. So when I ask the question, what type of data? Categorical or numerical? All right, well, I have the clipboard. What am I writing down? I'm writing down number of hours, right? So it's definitely numerical. How many sample groups? Well, there are males and females, and we seem to be comparing them to one another. So there's definitely two. And is it paired or not paired? Well, it can only be paired if number one, the sample sizes are the same. And then number two, if it makes sense to actually pair a piece of data in one group with a piece of data in the other. And I'd say the answer is no on both counts, right? Both of those have to be true. We don't even have, I don't think, the same. Yeah, it was 590 females, 588 males. So we're already out of being paired data from that. But it just wouldn't make sense to put a particular number of hours that a male spent and pair it up with a specific female in the other group. That just there's no connection between. All right, so we're definitely not paired. So this is a two independent mean test. Right, so I go to my formula sheet. And so here we are, two independent means, use the theory-based inference applet. All right, so we now know what we're doing. We don't need a bunch of formulas here. But what we do need to do is set up our hypotheses carefully, right? So I'm going to carefully define my parameters here. So I'm interested in the mean number of hours per week spent playing video games. Oops, still playing. By females. And we'll do mu m, same thing, but for males. And then when it comes time to set up our hypotheses, of course, a couple of things to remember about the null. The null is the no difference hypothesis, right? There's no difference in the average amount of time males and females spend playing video games. Also, it contains the equal sign. So either way, you would say this as your null hypothesis, that the two means are equal. For your alternative, though, they simply asked to see if it's different, right? That's what they asked us to figure out. And so I'm not going to be specific, even though I can look at this and just see, right? Looks like males from our sample are more than females in their hours per week. We're not going to be specific about that. We're just going to say not equal to. All right. Are the appropriate conditions met to conduct a hypothesis test? Well, it doesn't matter what type we're doing. Again, number one's the same, right? We are definitely sampling less than 10% of our population. And number two, numerical data. What's the other condition, right? It's not about successes and failures. That only applies to categorical data, right? This is about, is the population nearly normal? So what we would need to do is make a judgment about, is the amount of video games played by males and the amount of video games played by females, would those be normally distributed if I made a histogram of them? Well, what we'd like to be able to do is look at histograms of our sample data, and that can kind of give us a clue. We don't have that. But the reason I didn't give it to you is because, remember, there's kind of a, a way of making that second condition not matter very much with numerical data. And that is when your sample sizes are really large. So my guess is there probably is a pretty strong skew in the amount of time spent playing video games, right? Probably a pretty severe skew to the right for people who play just a ton. There's not many of them, but people who play a ton may be way far away from the bulk of people. So we'll just say this: the population, let's try that again. Population is likely skewed right, but we may still use the t distribution for our hypothesis test since the sample sizes are so large. Right? So we're okay on our conditions because of that. All right, so our p-value. So here, again, with the formula sheet, they don't give us formulas. They exist, of course, but I'm saying we don't need to worry about them. I'm okay with us using the theory-based applet. And by the way, all these tabs I keep pulling up, just like on the previous exam, they're going to be embedded within the question, so you don't need to worry about that. Um, so let's go with two means. And then we just fill in our information for each of the groups. 590 females, 588 for males. The mean is 9.2 for females and 16.4 for males. And then sample standard deviation, 2 and 14.1. Remember always to hit calculate afterward, and then we go with test of significance. And then remember, your job is to make this match up with your alternative. So you use not equal to the alternative, so make sure that's not equal to. And look at this. You get a test statistic of negative 10.04 and a p-value of 0, right? When you get a p-value of 0, what that's telling you is that if the null were true, samples like yours should never happen, right? They should never be that lopsided between males and females if the null were true. So that means we are going to definitely reject this null hypothesis, right? Since the p-value is definitely smaller than the level of significance. When you have a tiny p-value like that, I'd like to not only say that there is enough evidence, but I like to say there is strong evidence of a difference in the mean amount of time. And these are for, I guess, for youth, right? So we should be, in our conclusion, clear about that. Mean amount of time, female and male youth spend playing video games per week. Okay. All right, so let's check out another one here. So a doctor wants to know if a blood pressure medication is effective. 6 subjects have their blood pressures recorded. After 12 weeks on the medication, the same 6 subjects have their blood pressure recorded again. For this test, only systolic blood pressure is of concern. Assuming the appropriate conditions for inference are met, conduct a hypothesis test at the 5% level of significance to determine if the medication is effective. All right, so let's go through our flow chart. What type of data? We're recording systolic blood pressure. So on my clipboard, I'm writing down a bunch of numbers as I collect the data. So I'm definitely got numerical. How many sample groups? This is a little bit tricky because you're saying, well, there's just one group of people, but they were measured twice, right? Before and after. So I'm going to say 2 sample groups. Are they paired or not paired? Well, here's where it does make sense to pair them because it's the same people. Their blood pressure is being measured before and after, right? So we know we're doing a paired data test now. Okay, so that means our parameter value is this mean of differences, right? Between before and after. So we'll the average difference in systolic blood pressure after and before the medication. All right, so when it comes to a null hypothesis, right, an alternative hypothesis, right, we're thinking about the no difference hypothesis, right? Is the null, contains the equal sign. It's also the skeptical position, right? I'm skeptical that the medication is really helping. But let's think about we're trying to show that the medication is effective, right? So if it's effective, can we agree that that would mean that average is going down, right? So if you do after minus before, then going down, having a negative is good, right? That means it is effective. So we would want to say that the average of those differences is below 0. It's negative. Okay. I forgot to add a sentence to this. Oh, no, I did not forget. Good. On this particular one, you don't really have enough information. You need to make some plots and things like that, make a histogram in order to judge this. But it says assuming the appropriate conditions are met. So in this particular instance, I give you permission to just proceed um, as if the conditions are met. So if you're doing a paired data test and you're ready to get the p-value, let's remember that what you're doing is you're, again, using the theory-based applet, but you're going to go to a one mean test, right? This can be a little bit confusing because when I go back here, there's all sorts of information. There's the mean for the before group and the standard deviation for the before group, the mean for the after, the standard deviation for the after, but then it's the mean of the differences and the standard deviation of the differences. So what we need to understand is we are doing it for the differences. So ignore the stuff that goes above. All that really matters is that negative 1.33 and the 1.86 standard deviation of differences. So sample size is 6, negative 1.33, and standard deviation of 1.86. Calculate, and I'm going to switch this over to less than. And so there's our p-value, 0.0701. It's freezing. I apologize. Let me try. There we go. All right. P-value approximately 0.0701. Just a little bit too big, right? So we're going to fail to reject this null hypothesis, right? The p-value of 0.0701 is just a little bit bigger than our level of significance of 0.05, right? It's pretty close, but we're just saying that if the null were true, we'd expect samples like ours to pop up about 7% of the time anyway, and that's just not quite rare enough for me to throw away the idea that the null hypothesis is correct. All right. And then let's write out a clear conclusion about this, right? So there is not, right? We failed to reject, so there is not enough evidence 5% level of significance suggest that the alternative is true. But what was the alternative? The alternative is that the medication is effective. That's what we were trying to prove, right? The alternative is the thing we're trying to prove, to suggest that medication is effective. All right, let's do one more. It says, suppose that we want to know whether men or women are more likely to be living in poverty. In a study, it was found that 179 out of 1,400 men surveyed do, and 210 out of 1,390 women do. Does this data indicate that there is a significant difference in the poverty rate for men and women at the 5% level of significance? All right, so again, back to our flow chart. And you're not being given this flow chart once again, but if you go through this every time, you're just going to have it memorized. You're just going to know the questions to ask, and based on the answers to those questions, you're going to know what that means, right? If you just commit to doing this every time you do one of these practice problems for the exam. So what type of data has been collected? I've got the clipboard. I'm interviewing people, or I'm collecting data on people about poverty, right? But poverty, that's something that this is a little bit tricky because you might say, well, aren't you writing down their income or how much money they have? Well, maybe, but ultimately, I'm writing down whether or not each person's in poverty, right? Because they gave me a count. This many are in poverty out of everyone that we talked to. So the thing I'm ultimately writing down is yes, poverty, no poverty, right? That's what I'm writing down. So that means it's categorical data. How many sample groups? Well, clearly two, because we're comparing men and women, right? So here's where we're doing a two proportion test, right? And we're going to use the theory-based apple. All right, so let's go execute that. So since we've got two groups and we've established we're doing proportions, let's go ahead and do PW and PM. The proportion, let's look at R, let's try that again. Proportion of women living in poverty, and the proportion of men living in poverty. So our null hypothesis is that, well, that's going to contain the equal sign. There's no difference between the proportion of women and men who live in poverty. And just remember also, this is also a perfectly legitimate way to write it, right? It's the same thing. Okay, say it either way. And then we want to try to prove that there is a difference, right? That's what we're trying to prove. So that would be PW does not equal PM, or PW minus PM is not zero, right? That's what it would mean. It would be if the poverty rates were different. Okay. Now, for this next part, checking the conditions. First condition, just like all the rest of the problems we've done, no problem. We are, in fact, sampling less than 10% men and women. No problem there. Now, in number two, remember, we're supposed to be checking a success failure condition anytime it's proportions. Now, this is a little bit tricky because the success failure condition means that based upon my sample sizes, I need to be expecting at least 10 successes and 10 failures. Now, on the one hand, the numbers involved here, it's a no brainer. Of course, I'm expecting at least 10 successes and 10 failures because I can see I actually got 179 in one group and 210 in the other. So that's enough. So, like, if you got numbers that were that big, I would be okay with you just saying we have more than enough successes and failures. However, sometimes it is a closer call and we have to have some calculations. And so I'm going to pretend like I don't notice that. I'm going to go ahead and go through those calculations for us here. So let's keep in mind, right? I'm just doing this over on the side. We can calculate the sample proportion for women, right? That's what, 210 out of 1390. When I do that, about 0.151. And I can do that for men too. 179 out of 1400. So 0.128. So clearly a difference between them, right? So how do we say that how many successes we expect? Well, we're assuming that the null is true, right? So I'll remind you just briefly in our problem number two, when we checked this condition, we took our null value and we plugged it in and multiplied it by our sample size. I'd like to do something similar here. However, we don't have a null value like we did in that earlier one. So the idea here is that we're assuming the two proportions are the same. So our best guess for what they are both equal to is just kind of splitting the difference, so to speak, between the two samples. So this is where we use our pooled proportion, we call it. So you just kind of pool these number of successes together and you pool the sample sizes together. And when you do that, you get a number that's between the two individual samples. Just kind of splitting the difference. So 0.139. So 0.139. So that's what I'm going to use, right? This 0.139. Let me write it. It's a little easier to see. That's what I'm going to use when I'm testing over here. Again, I know that there's not a lot of suspense here, but we'll go 0.139 times 1390, right? And that's 193. And we'll do 0.139 times 1400. Now, technically, I should predict the number of failures in addition to the number of successes, but here's the thing. The probability of failure is a lot higher than the probability of success, and so it's not really necessary. So this checks out, right? We expect at least 10 successes and 10 failures. All right. So now that we've got that out of the way, we are allowed to go and use the theory-based applet. So I go back here and I'm going to select two proportions. So our sample sizes are, let's see, 1390 for women, 1400 for men, 210 for women, 179 for men. Look at that. There's the sample proportions we came up with. And then we're going to make our alternative match with our alternative on paper. So we go not equal to. So here, with the two-tailed test, my p-value is 0.0766. Similar to our last problem, it's a somewhat small p-value, but just not quite small enough, right? So we fail to reject the null. Because our p-value of 0.0766 is greater than our level of significance of 0.05. And so we can see there is not, right? We failed to reject, so there is not enough evidence for our alternative hypothesis. And our alternative hypothesis that there is a difference, right? There is a difference in poverty rate between men. Okay. So I said at the beginning, there's really 7 things I could ask you to do. 2 different types of confidence intervals, 5 different types of hypothesis test. So in terms of confidence intervals, we did a confidence interval for a mean. We did not do one for a proportion, but that's certainly fair for me to ask of you. For our hypothesis tests, right, we did a single proportion. We did a paired data to mean test, an unpaired data mean test, and 2 proportions. The only one we didn't do is a single mean test, but of course that's a fair one as well. You're going to have lots of examples of these as you go through your inference review packet. So I just want to emphasize again, going back here, get started on this early. Watch this video ahead of time. I mean, if that flow chart really made sense to you, I kind of redo the flow chart here. So if you want to fast forward through that, if you're feeling really comfortable, that's fine. But definitely at least watch the beginning where I explain the instructions here and what I'm asking you to do. So that way those parts make plenty of sense. Here's the key for it right underneath. And then finally, what I want to say is you can see how my tabs are open here to these different calculators. And you should have them open as you're walking through the inference review problems for sure. But what I guess I also want to just let you know is that I think I already said this, that these calculators will be on the exam, but there will be times where I will put more than one. So let me give you an example. Let's say I ask you a question just like our first one, just like this. One of the things I'm going to want to know from you is if you realize whether you're supposed to use T or Z, right? Based upon this type of a problem, do you know which one is the appropriate one to use? So on the test, I would give you both a normal probability calculator and a T probability calculator in that problem, and you got to decide which is the right one to use. Okay, just be ready for that and aware of that. Okay, and then finally, here's the last thing I want to say before I let you go, is In that review packet, so going back here again, what you'll see is that you have problems with just a blank underneath, okay? The problems that we just did in practice had definitely, parts A, B, and C. The exam will be more like these, right? More like number 2 here, where I say, okay, state the null and alternative hypothesis for me. Give me the standard error, give me the test statistic. So it will be more like number 2 here than it is like this problem where it's just blank underneath. But I think doing it without every little step being asked of you, step by step, is going to be really good for you in understanding the process better. Okay. So I don't want you to panic when you see these just, the blanks underneath of these problems, because I will ask them in some steps, but making yourself do it this way where it's just like, okay, what do I do next? Okay, I got to do the hypotheses. Okay, then I got to check my conditions. Then I've got to do this. Then I've got to do that. You having to go through that will help you in the process of preparing and help you feel more confident going into that exam. All right, so please reach out as you have questions throughout your review process. I do have some different student hours this week. Just as a reminder, I sent a message about that. So my Friday student hours, unfortunately, are a little bit more restricted than they normally are. So, but I have extra hours Wednesday and Thursday. So please stop by with any questions you have. And of course, you can also post questions to the homework form. So don't hesitate to do that. Oops, I'm sorry, I wasn't sharing my screen there. Okay, let's try this one last time. Okay, here we go. Here's the hours for Wednesday and Thursday. A little bit restricted on my Friday hours, you can see. But yeah, use the homework forum, send me messages, drop by student hours. I'm here to help. All right, have a great day.